joining. It's a great pleasure to introduce Niccolo Veronesi, which is here from Washington State University. Nico did his undergrad and master degrees at the University of Bologna, and he may tell you that this is the oldest university in the world. Then he did his PhD at the Leiden Observatory under Professor Elena Rossi, where he put the first observational constraints on the formation channel of stellar mass binary black holes related to AGN. And then I had the good fortune to recruit him at WSU to come work with me. And now he's working on preparations for the first presence and detection of a supermassive black hole binary. He will tell you both about stellar mass black holes and supermassive ones.
Okay, thank you very much, Maria. I'm very happy to be here. And so, yeah, before I start, please feel free to interrupt me, raise your hand whenever there is a curiosity or a question that you want to ask. Also from Zoom, I asked Carolina to interrupt me in case someone writes something on the chat. So yeah, as Maria introduced, today we're going to talk about, in general, binary black holes and try to find out where they are and merge. No? Yes. So yeah, the talk will be divided in two main parts. The first part, we're going to talk about stellar mass black holes. Just to be clear, the ones that have been detected by LIGO and Virgo and CAGRA. And the second part, we're going to talk about the supermassive black hole binaries, which is a completely different astrophysical question that we're asking, but same, yeah? Yeah. That's maybe because no, let me share. Yeah. Is this working? Okay. Okay, so let me click back. Okay, so let's start with the first part. Yeah, just I'm sure that I don't have to to go in the detail of this for any of you, but there are several types of black holes. Starting from stellar mass black holes, just to be clear here, I'm talking about black holes that are lighter than 100 times the sun, and they come from usually they are the remnant of very massive stars. Then on the other end of the mass spectrum, we have the supermassive black holes, say masses bigger than 1 million solar masses, and then somewhere in between we have the intermediate mass black holes. There are, for each of these families of black holes, we have different questions that are still needing an answer. The one, according to me, that is very interesting regarding stellar mass black holes is where do they merge? And this is what we're going to talk about in the first part of this talk. So when black holes form a very tight binary system and they in spiral, they emit gravitational waves that are ripple in space-time and that travel at the speed of light. And they can be detected by ground-based interferometers like the ones of the LIGO, Virgo, and CAGRA collaboration. Just to have an idea, I always picture gravitational waves like sound, while light and every electromagnetic wave, I picture it differently. And why is this? Well, because just like sound propagates through air from my mouth to your eardrums, and it's also made by air, so it's like fluctuations in the density of air that I am generating and they are reaching your ears. Gravitational waves are just like that, but instead of air, you have space-time. So you're gonna hear me saying we hear gravitational waves instead of we see them, because we don't. So the LIGO, Virgo, and CAGRA collaboration is formed by LIGO, Virgo, and CAGRA. They have been, so these three a total of 4 interferometers. Here you see the ones of LIGO and Virgo. They have been operating since 2015, when we had the first direct detection of a gravitational wave. And they will be operating, it's actually very hard to know for sure. I think no one does, but at least here it says 2029. We are now in the period in which 04, so the 4th observing run is ongoing, while the first 3 have already been completed, and in between different observing runs, there are always improvements in the sensitivity of the detectors that lead to more detections and further detections. These are the 90 confident mergers that have been detected by LIGO, Virgo, and Kagra collaboration in the first 3 observing runs. Per each triplet you have, so this is chronological order on the x-axis and the mass on the y-axis. Per each triplet, you have the masses of the 2 black holes merging and the mass of the remnant. Just to give you an idea, those were the ones detected during the first 2 observing runs, and then there was an update of the whole instrumentation, and these were the ones detected during the 3rd one, and I'm not sure, but at least double this amount are being detected during the 4th observing run. So we are getting more and more observations as we speak. However, how these binary forms and where they are, it's still very unclear and very debated. So how do these binaries form? There are 2 main ideas, 2 main options. Maybe the answer will be lying in the middle of these 2. But option 1 is these binary black holes form from an isolated binary star. So you have like 2 stars, both massive enough to produce a black hole at the end of their life. And at the end of their life, they end up being a binary black hole, which is tight enough in order to emit gravitational waves until the merger. Second option is you don't have an isolated binary star. You have an environment which is dynamically dense, meaning that gravitational interaction, it's so dense of object that gravitational interactions between these objects are frequent with respect to Hubble time, let's say. So we're talking about maybe say 1,000 solar masses of objects in 1 cubic parsec. So we're talking about globular clusters, we're talking about nuclear star clusters. And in these scenarios, long story short, all these gravitational interactions between these objects, for example, black holes, can lead to the formation of binaries, again, that are tight enough in order to produce gravitational waves and then merge and then be detected by the LIGO, Virgo, and Kagra collaboration. There's an option 2A, which is, so still a dense dynamical environment, but this being an AGN disk. What are the main differences between an AGN disk and a regular nuclear star cluster in this case? Well, for what we are interested into is that the AGN disk is a 2-dimensional object. So you have all your black holes that you're interested into in a disk and not in a sphere. And there is interaction between the compact objects and the gas. And this physics was first done for protoplanetary disks and motion of compact objects inside of them. But the idea is the same, meaning that it's very common for compact objects in a gaseous environment to migrate inward, usually, in this disk, therefore increasing the density even more of compact objects, therefore facilitating maybe the formation of these binaries that we have seen merging, that we've heard, sorry, merging. So the idea is maybe some of the gravitational waves that we have detected come from binaries that were in AGN disks. Now, we have 90 detections. How comes that we cannot tell where these mergers happened? Well, this is the reason. This is a typical localization area for one of the detections. And again, it's just like hearing. If you are in a dark environment, like in a dark room, and someone claps their hand, if I had you close your eyes and one of you clapped their hands, if you're far enough from this person, you wouldn't know which person clapped their hands. And it's the same here. So we are hearing gravitational waves, but we cannot be very sure about where in the universe this merger happened. And we are not very sure, I mean, we are really, really not sure. This that I'm showing you is the cumulative distribution function of the size of the typical 90% localization volume of the gravitational wave detections. So we are saying that the median size for these blobs, these bubbles in the universe, is 10 to the 8.5 megaparsec cubes. Just to give you an idea, if you take very luminous AGN, we are talking about densities of 10 to the -7 objects per megaparsec cube. So if you take very rare objects in the universe, you find one every 10 to the 7 megaparsec cube. Which means that in 85% of the cases, because this is more or less 15, so in 85% of the cases, the localization volumes of gravitational waves are so big that by chance, just because of like random scrambling of the universe, one of these AGN will be in your localization volume without any existing causal relation between the two things. And this makes it very hard because, again, I'm now talking about rare objects. So think about how many galaxies you have in 1 gigaparsec cube, thousands and thousands. So it's very hard to pinpoint which one was the source of the gravitational wave. I think there are 3 ways of trying to understand how binaries formed, how binaries of stellar mass black hole formed. One is this. So you hear the gravitational wave, and somehow you also see light coming from the same source. This has happened once, as you might know, with gravitational wave GW 170817, so 17th of August 2017. And those were 2 neutron stars, not 2 black holes. But you had light and gravitational waves coming from the same object. And there was really a gold mine for, for multi-messenger astronomy, and they put very interesting constraints regarding not only astronomy, but also fundamental physics, cosmology. You can do a lot of things if you can detect gravitational waves and light coming from the same object. However, in general, binary black holes are not expected to produce any light. So this is very hard. This is a very hard, very challenging way to detect light and gravitational waves coming from the same object. However, people claim that if it's in an AGN disk, that maybe this merger can shock the gas of the AGN disk and therefore produce flares of light. There have been a lot of talking about this. I won't touch the subject, but if you're curious about that, you can ask me whenever. Second way is you choose your favorite formation scenario, say, for example, AGN disks. You say, okay, binaries form in AGN disks. So you model your AGN disk, you put black holes inside of it, and you say, okay, then the binaries that I expect to be formed in this environment should have these masses, for example, big masses, due to mass segregation, should have spins that are oriented like this or like that, maybe oriented in the same way as the AGN disk, or should have this mass ratio, so how massive is this correspond with respect to this. So you can build expectation values for your binary parameters, and then you can go check in the data if, in the observed data, if there are binaries that really look like the ones that should be forming your favorite formation scenario. Third way is, again, you choose your potential host. For example, AGN disks, here are the pink markers, and you cross-match the positions of the AGN disk with the localization volumes of gravitational waves. And you check if there is a spatial correlation between these two things. And this is what I worked on in the last years. So the question that we are now trying to answering is, what is the fractional contribution of the AGN channel to the total merger rate? Meaning, out of the 90, more or less, I will explain better, that we have detected, how many of those were originated in a gravitational, in an AGN disk? So these slides, the following slides can be like not super easy to see, but just listen to me. It's not, you don't have to understand all that it's written, but just the idea of how it works. So how does this analysis work? This is our scenario. We have AGN disks with a number density n, and you have, for example, say one gravitational wave event with a localization volume of V90. Then you build your likelihood function, which is a function only of FAGN, which is what we were saying earlier, the fraction of gravitational wave events that happen in an AGN. And you build this likelihood function. Now, how should you picture this function? As separated in two parts. One has this, what the so-called signal probability density, and the other one, the background probability density. These functions are like this. If the placement of the localization volume with respect to the AGN population suggests an AGN origin of the gravitational wave, SI is big, especially bigger than BI. Vice versa, if the placement of these two things don't speak to each other, then the background probability density gets higher. So if you put, if you draw a plot of the likelihood with respect to FAGN, of course, the maximum value is 1. For each gravitational wave event, if SI is bigger than BI, then the likelihood peaks at 1, meaning that this specific only one gravitational wave event is likely to have come from an AGN. Vice versa, if BI is bigger than SI, then this peaks at 0. So you do this calculation, you do it for every gravitational wave event, you sum you sum the log likelihoods, and then you have this plot, but for the overall population of gravitational wave events. Again, not going into the detail, but how these functions look is like this. And what we take into account, what is very important to take into account in this analysis is the completeness of your AGN catalog. Actually, time-wise, most of my work went into putting a number here. So meaning, how many AGN am I missing? How many AGN are in the universe but not in my catalog? Because say that one of them generated my gravitational wave, then I will associate that gravitational wave to not coming from an AGN, while actually it was. So you have to take this into account, and it's very important for this kind of analysis. And then we take into account also the exact position of the AGN inside the localization volume, whether it's on the outskirts or in the hottest part of the localization volume of the gravitational wave. Then you maximize your likelihood and you applied to observed data and you get results. This is the observed data. So this is again chronological order. This is just like indices of the gravitational wave events. And this is their luminosity distance measured from Earth. These are the gravitational wave events that we use. These ones are the ones coming from the first 3 observing runs. These are the ones coming from the 4th observing run up to June 1st, 2024. Caveat, maybe not all of these will make it to the final catalog that will be out sometime late 2026, I would say. But these are the ones that were detected before June 1st, and they have been associated a preliminary chance of being binary black holes bigger than 99%. So again, maybe out of these, not all of them will be in the final catalog, but still I decide to trust them. And then we have to cross-match it with AGN catalog. We use the Quaya, which is a catalog coming from the AGN catalog of Gaia, but reworked by the team of Kate Story-Fisher. And so these are all objects that were measured by Quaya, by Gaia, and by WISE. And yeah, up to 20.5 magnitudes in G. And we cross-matched these with our 159 gravitational wave events. Again, this is just luminosity distance as a function of size of the localization volume. Of course, you can see that the further I detect the gravitational wave from, the bigger the uncertainty in its localization will be. I think it makes sense. Okay, we'll go very quick on this slide, but just to show, as I told you, we calculated the completeness of Quaya as a function of redshift and the luminosity of the AGN. This plot is showing how many objects we have in Quaya with respect to what you expect from SDSS and from fiducial luminosity, quasi-luminosity functions. And you can see that especially the brightest, in the brightest case, we are basically complete out to redshift 1.5. And then the dimmer you go, the sooner you start to measure less objects with respect to what you measure from luminosity functions. But this also makes sense because they get dimmer and therefore I cannot detect them from far away. Okay. Okay. These are the results. How to read this plot? So here I'm showing the bolometric luminosity of your AGN catalog doing different cuts. And on the x-axis, you have FAGN, the fraction of detected gravitational wave events that happened in an AGN. The blue region, this, is the region of this parameter space that our analysis rejects with a 95% credible level. What does it mean? That we are 95% sure that not more than 21% of the detected gravitational waves come from AGN brighter than 10 to the 44.5 ergs per second. And then if you want to go up one level, we are 95% sure that not more than 11% come from AGN brighter than 10 to the 45 ergs per second. This is so this dashed line corresponds to the results of a previous work that we did, and this dashed line corresponds to, yes, the first observational constraint on the origin of stellar mass black holes. And yeah, this was just to show that using a better catalog, say Quaya, and more gravitational wave events, we were able to put much tighter constraints. So to answer our question, what is the fractional contribution of the AGN formation channel? The answer is likely not more than 20%. But the literature in this is very active lately. Very quickly, this work is keeping on going. A student in Leiden, Lucas Pau, in his master thesis, actually, his job was basically to do what we did, but not only taking into account the localization of the gravitational wave events, but also the distributions over the binary parameters, so the distribution of masses, the distribution of spins, and so on and so forth. So basically, in his first months, he took the likelihood function that I showed you earlier, which was derived by us from like in a rather empirical way, and he rederived that basically from Bayes' theorem, and then he built a much heavier likelihood that, however, takes into account every parameter that you want. You can take that into account, and every parameter that you are not interested into, you can marginalize over it. So basically, the likelihood that we used was this one, in which we marginalized over everything but the localization of the AGN. Okay, so I think it's now time to go to the second part of the talk. So we go up 7 orders of magnitudes in mass, and we're now talking about supermassive black hole binaries and the properties of the host galaxies in which they are. This work has been recently, like 2 weeks ago, posted on Archive in collaboration with, me and Maria, in collaboration with Stephen Taylor, Jesse Runot, and Daniel Dorescio. And yeah, so far we have talked about this, okay? So this is the LIGO-like detector, which is detecting merging of stellar mass black holes. And we are talking about gravitational waves with a frequency of 10 to 1,000 hertz. We go now up 7 orders of magnitudes in mass, and more or less 7 orders of magnitudes down in frequency. So we are now talking about nanohertz signals of supermassive black holes that are in spiraling. Also, another difference, which I think is important, we hear the last seconds of life of these binaries, so the so-called chirping, when they get very close to each other and then they merge. We detect these binaries orbiting in such a manner that, yes, they are emitting gravitational waves, but their frequency so the frequency of this orbital motion don't change usually on the lifetime of over the lifetime of a human being. Okay, so these are basically monochromatic waves that are coming from supermassive black holes. How do we detect them? I don't know how many of you are familiar with pulsar timing arrays or PTAs, but I'm sure that all of you are familiar with neutron star and pulsars. So pulsars are these objects that emit a very thin cone of light, that if it meets Earth, it creates this lighthouse effect. So we see this pulse, hence the name, with a very, very high frequency, but more importantly, with a very precise frequency. So pulsars are very, very, very predictable. We can calculate very well when the next pulse is going to arrive. And taking into account the fact that the pulsars slowly slow down and they might be in a binary system, you can take that into account and predict when the next pulse is going to arrive with a very high precision. Meaning that if there is a displacement between when you see the pulse and when you were expecting to see the pulse, means that something is going on. What might it be? It might be that a gravitational wave is passing between the pulsar and Earth, stretching and squeezing the space-time, therefore shifting the time of arrival of this signal. This is how PTA works. Very long story, very short. But I don't know much more of the instrumentation, so yeah, I can try to answer any question, but I don't give it for granted. Anyway, so what are we hearing? Maybe two galaxies merge. Now the question is, after we see the two galaxies merging, how much time does it take for the two central supermassive black holes to also form a binary that emits gravitational waves? Does it form a binary at all? Do the central mass black hole get close enough to, generate gravitational waves? I would say yes, but I will explain this in a moment. And yeah, so this is the stages. So you have galaxy mergers and then the black holes that get closer and closer to each other until they form a binary that emits gravitational waves. Now, we have in 2020, I mean, not we, some people have detected a gravitational wave background in 2023. What does it mean? It means that we are hearing, most likely, a lot of these binaries that are all orbiting somewhere in the universe. Their signal gets to Earth, let's say, gets detected by PTAs, but we are hearing a crowd of people talking to each other without being able to separate any voice from the crowd. Okay, we are hearing the orchestra playing without hearing the soloist. So we know that there are people talking. We know that most likely, we know that there are supermassive black holes orbiting, binaries orbiting around, orbiting. But we still have to hear one, the loudest one. We still have to hear that. So, yeah, so this is just the power spectrum of this background. So these a lot of binaries that are orbiting without us being able to pinpoint one. So the question is, will we hear the soloist? So this plot is basically showing you the sensitivity of PTA as a function of the frequency. Okay, every pink marker is a binary. Whenever you have a binary that is above the sensitivity, it will be resolved. We will be able to see, okay, there is a binary somewhere over there emitting with this frequency. And these are the masses of the system. Now, basically, keep on listening with PTA. What we are doing is moving this line down, 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 until, again, we are waiting for the first one of these to pop up and go above the sensitivity curve. The expectation is that this will happen in the next 5 to 10 years. Then, what do? So say that we resolve the first supermassive black hole binary. These are the typical masses that we are expecting and typical luminosity distance. So we are talking hundreds to 1,000 megaparsec and 10 to the 9, more or less, solar masses. Then you can localize badly, like we are used to in gravitational waves, where the gravitational wave is coming from, so where the binary is, and you can select all the galaxies that are in that localization volume to try to, look for the actual host of the binary. Then, once you have a selection of binaries, galaxies, you can check each and every one of them through archival data or new observations to look for patterns in their signal that can hint to the presence of a supermassive black hole binary in their center. For example, you can look at the photometric variability in the case, for example, in which the binary has at least one active black hole. Then, if you do this, if you're actually able to pinpoint the actual host, then you can have fun with multi-messenger stuff. You can put constraints on actually a lot of things. So the dynamics of the binary, density of interstellar medium, timescales of how do you say, mass segregation, but that wasn't the word I was looking for, but anyway. And then you can repeat this for every binary that in the future will be detectable. This is always the problem, right? So here I'm showing you probability, like the distribution of the localization areas that we will be dealing with. So hundreds to thousands of square degrees in the sky. So in these localization areas, we have a lot of galaxies. How do we find the actual one, the actual host of the merger? Again, as I was saying, you must select the most, the most promising candidates. You can do this by selecting them with sky position, so they have to be in the right position in the sky. They have to be at a certain distance from Earth. And you can try to say, okay, now I want only the ones for which we have a precise measurement of the central mass of the black hole, which is in agreement with what has been measured for the supermassive black hole binary. However, this precise measurement is not available for many galaxies, and especially we have it only for close-by binaries. One quantity that we have for a lot of galaxies in the universe is their apparent magnitude. So the question is, can we link the gravitational waves that we detect and its properties to the apparent magnitudes that we expect for the host galaxy? Yeah. So very quickly, this is so all the stars, squares, and round markers are pulsars that we use in our work and to simulate different scenarios of pulsar timing arrays. And the grayscale that you see is how well we can hear binaries in that region of the sky. This is basically the antenna pattern of PTAs. So how well you hear as a function of the sky position. So we calculated this. And I think I'm going to skip this. Yeah. And then we placed binaries in the best or the worst sky position in which they can be. And we calculated how far we can hear them with PTAs. Now, this plot is, so focus on the gray and black lines that are regarding PTA. And this is how far in luminosity, in megaparsec, log of megaparsec, we can hear a binary as a function of its total mass with PTAs, okay? So we're talking about binaries that are heavier than 10 to the 8.6, up to, we can hear them, in the best case, up to redshift, say, around 0.5. Okay, then what you can do is to take your gravitational wave signal, you calculate you have a distribution on the mass of the binary, and you can use all the scaling relations that you need in order to translate the mass of the central mass black hole, central supermassive black hole, into expectation value for the magnitudes of the host galaxy. So you translate mass of the black hole into mass of the bulge of the galaxy into total stellar mass of the galaxy, total stellar mass into luminosity in the K band, in the infrared, luminosity in the infrared into magnitudes in other bands. Of course, taking into account every uncertainty that comes from every one of these steps. And these lines are showing these results. So basically, you are seeing, for example, say, WISE, so the red line here, This is how far WISE can, so in the infrared, can see a galaxy as a function of the estimated mass of its supermassive black hole. What is this plot telling us? So whatever is in this region of the plot is what we can hear with PTA. Whatever is below this red line is what we can see with WISE. So what this plot is telling us is that whenever we will have the first detection of a supermassive black hole binary, the host is very likely already in WISE and in supercosmos and more very likely in 2 mass. So we already know the host. We just don't know that it is the host. So, okay, yeah, sorry, this is the same thing, but if you assume the host environment to have an AGN, in that case, you go from the mass of the supermassive black hole to the bolometric luminosity, and from the bolometric luminosity to the luminosity in each band, and then the magnitude in each band. So what we will be able to do is to take the gravitational wave signal, so mass, frequency, and the amplitude of the wave, translating it into total mass of the binary and how far it is from Earth, and translating this information into magnitude of the potential host. So, and this is an example. So this is very small labels, but you have mass, luminosity distance, magnitude in K, magnitude in W1, magnitude in B for a simulated gravitational wave event. Meaning that now we will be able to, whenever you have a detection, not only select the potential hosts given their position and their distance, but also given their apparent magnitudes, which we have for millions and millions of galaxies already. So we can refine this method for looking for the host. So yeah, this is long story short, what we can see, actually, what we can hear with PTA, we can also see with all the most of the all sky surveys that are already available. The next steps that we are starting to take now for the next project is to do this, but in a more realistic environment. So we build astrophysically motivated populations of binaries. We simulate the detection of the loudest ones, so the first ones that will be detected. We calculate their simulated localization areas, and we cross-match them with real galaxy catalogs, performing all the selections also in magnitude, and check how many galaxies we will end up having to be prepared when the first binary will be detected. Hopefully not too many years, 5 to 10. That's it. Thank you very much. Thank you.
Hi.
Hi.
Thank you very much.
Thank you.
Just out of curiosity, for instance, the AGN disk scenario, way that you can, look through simulations, or in general in your work, there is any way that simulations can be helpful?
You mean like hydrodynamical simulations of AGN disks? There are a lot of works on this. So the answer is yes. You can put constraints using simulations. However, those simulations, I think there are the two main things that you have to take into account is that I think a lot of you in the audience know much better than I do. There are a lot of uncertainties in the physics of AGN disks. And as soon as you tweak one of those parameters, your simulations regarding populations of compact objects can vary a lot. But still, there are a lot of very interesting works on this. And the other thing is that even if you build your perfect model, still, whenever you detect a gravitational wave, the uncertainties on the binary parameters, masses and spin, or spin magnitude and spin orientation, for example, are of the order of 10%. So you have very broad distribution. So even if you have the best model, the detections still are, the constraints are broad enough for you to be able to fit whatever you want inside of them. These are the two main limiting things, but more detections, more data, better constraints also on that end. Yeah. Thank you.
Many questions, very interesting.
Thank you.
So let me ask two questions, one for the first part, one for the second. So for the first part, following from the previous question, is there any area of the parameter space of black hole mass distribution or black hole speeds that you can predict from the accretion disk scenario and is not allowed by regular stellar evolution patterns?
Okay, short answer, no. Slightly longer answer, kind of. So you have, I can give you my favorite. So the mass spectrum that has been predicted, so this is probability, and this is mass. It looks kind of like this. So this is the probability distribution of masses of stellar mass black holes, where this is 8, 5 to 10, I don't remember exactly. This is 35, and this is above 50. Now, this region, according to most stellar evolution scenarios, shouldn't exist. Because at that point, depends. Yeah, you see what I'm saying when the short answer is no. So, according to many people, that shouldn't exist because then the star should be so big that you have the so-called pair instability supernova, so a supernova that doesn't leave any remnant. However, you can tilt the reaction efficiencies in your core to make it so that you can also allow these very high masses. Because the other option would be those masses, so these black holes that we measure of say 70 solar masses were already the result of a previous merger that ends up in a new merger in the so-called hierarchical merger scenario. So again, the short answer is no, but if you go to any conference regarding this, the focus is really in, and I like this, is on looking for these smoking guns. So like looking for one thing that you can explain with one channel and not the others. Yeah, I could give you other examples, but maybe another time. But yeah.
Is actually have enough events, so you see an excess of gravitational wave events associated with AGN.
Yeah.
You don't really know, because even if you see a gravitational wave event in an AGN galaxy, you don't know if the gravitational wave event is coming from the accretion disk or
correct.
coming from the post galaxy. You have no idea.
If,
no resolution.
Absolutely, I totally agree. In fact, one of the things here is that we say that most likely not more than 10% of the events come from an AGN, but also AGN are more or less 10% of the galaxies. So we are now hitting a wall here, like you cannot go below that. So yeah.
It's your just coincidence.
Basically, yes. Like, yeah. Do you have a...
Let me ask the second question. Okay, we can go to the next question.
Thank you.
And discussion.
Yeah.
And I was thinking, is there a way where should they so I think it's like creating a general where they like few stuff for me.
Mhm.
And what this
Mm.
like, and also
Mhm.
using galaxy catalogs
Mhm.
that are not only for ATN. So you have there are galaxy catalogs that have ATN, Stanford,
Mhm.
so what is your that would be
Yes, so that's a very interesting point. I think I can answer you in two ways. So the easy way would be to basically this likelihood can be used for whenever you want to check for the match between something that is not well localized and rare sources, rare like gravitational wave event and AGN. But you can change gravitational wave event with neutrinos or whatever you want, and AGN with anything you want that it's point source. And so you can do basically the same analysis parallel for AGN and for starburst galaxies or E plus A galaxy or changing look AGN, like all the potential hosts that you are interested into, and see how the results match with each other. The other option is that in this case, the background hypothesis is basically that if the background scenario is the true one, so the gravitational wave doesn't come from an AGN, then how this works is that it could come from anywhere else in the localization volume. So you take the probability and you spread it on the whole localization volume equally. One way to address what you were suggesting is instead of doing this, turning this into saying if it doesn't come from an AGN, it still has to come from a galaxy. And so instead of making it continuous over the volume, making it discrete all the other galaxies. Yeah.
also that
Yeah.
information rates.
Yeah, yeah. You can choose. Mhm.
So you can based on
Yeah, the only thing, I mean, I totally agree. The only thing in that case would be that your final answer would be something like it's more likely that it comes from AGN with respect to starburst, right? You're not testing the general thing. You're just comparing two models in that case. But if that's what you want to do, yeah, this can be turned into that.
But
Absolutely.
it doesn't have to become starburst because
Yeah, yeah, yeah.
it can be like any stellar origin of a gravitation.
Yeah, yeah. You can do with whatever you want. The only thing is that why are AGN cool with this? Because they are an interesting physical environment and they are kind of rare and easy to detect. So you can decently characterize their catalogs. If you try to do the same with regular galaxies, then you have many more galaxies in your localization volume, so it's much more noisy and it's much harder to estimate the completeness, but totally possible.
But it's an interesting idea because this way you can increase your contrast
Mhm.
between the AGN and the other galaxies.
Yeah.
So if indeed the signal is coming from the heavy, then it's unlikely to come from the other galaxies because they don't have the right properties.
Mhm.
Then you will see it.
Yeah, absolutely. Yeah, I totally agree. And these properties of the galaxies are also part of these parameters that are being taken into account in this gigantic work that Lucas is doing. I'm super curious about the results that he will obtain. But yeah, basically from this galaxy, you have in this likelihood, you have all the parameters of the binary and all of the parameters of the potential hosts, and you choose what to marginalize over. So if you don't care about something, you marginalize over it. Otherwise, you can keep whatever you
Can I ask something related to that?
want.
Saying so, which parameters for the binary are important for this?
Masses.
The
Yeah.
masses or the
So in general, total mass of the binary, mass ratios, because people suggest that in the AGN disk, you should have an unequal mass ratio. And also because So first, it's easier to model the masses, like from your physical environment, like for your physical model of the environment, and in the data. And this goes back to the first question. In the data, masses are better constraints than speeds. So those are the ones that, yeah, you can build your likelihood, but then actually the data will be able to inform the likelihood even more if you use the masses. Yeah.
That's the question.
Yeah.
Yeah, let's talk supermassive.
Exactly. So when you predict the observables from when you do this forward modeling,
Yeah.
so you predict the observables based on the binary black hole supermassive black hole.
Yeah.
Now the scalings that we have that we know are based on single black hole.
Mhm. Yeah.
So we have scaling relations between supermassive black holes and Bohr's mass, supermassive black holes and velocity dispersion, and that
Yeah.
cell mass. So
Yeah.
how do you translate? How do you make the step
Mhm.
from a binary supermassive black hole
Mhm.
to those scaling relations?
Mhm. Correct me if I'm wrong, but the thing is that you don't do that step because so these binaries are very tight. So the typical distance is percent level of parsec. So they're very, very tight. The black holes are very, very close to each other. And all those measurements are dynamical measurements. So it doesn't really matter if you have, so you would have the same velocity dispersion with a single object or with a binary object, which is very tight. You would have the same velocity dispersion for the stars that are around, like in a much bigger scale of the galaxy.
But this doesn't have the implicit assumption that all supermassive black holes that we observe
Mhm.
and have been used for measuring those scaling relations
Mhm.
are either the sum of binary black holes or are the product of binary holes.
Mhm. But let me know if I answer your question. But the thing is that, so when you use this translation to get the Burge mass, you use scaling relations that were done, like were fitted on observations that could really tell the difference between yeah.
But now you translate that supermassive black hole
Mhm.
we measure
Yeah.
to a
Yeah.
total binary mass.
Yes.
To the total mass of the binary black hole.
Yes.
So effectively now, if you use blindly this scaling relation,
Yes.
effectively you assume that all local galaxies or all galaxies that we use so
Mhm.
to measure those scaling relations
Sorry, I now see what you meant. Yeah, yeah. No, go on, please.
are either the product of supermassive black hole mergers that keep them, effectively you have mass conservation,
Mhm.
or what we see locally is binary black holes that we don't solve.
Correct. That is correct. Yeah, yeah, yeah. Yeah, sorry, I took one more step on. Yeah, yeah, yeah. So this is the total mass of whatever you have at the center of the galaxy.
Okay. That's next.
Thank you.